Okay, now let's go ahead and start our feature engineering process, as well as getting rid of features that are not going to be useful to us. So we're going to start working with this feature data, and I always like to kind of review the data frame itself. So something we can drop right away is this ID. This ID is some sort of unique ID. There's no trend to it, and if there is, we probably don't really understand it based off this number itself. So I will just say df is equal to df.drop, and then go ahead and drop that ID column. And that's along axis is equal to 1. So we go ahead and just drop that ID column, and the next thing we're going to do is check out the date column. So if we take a look at this date column, right now it looks to be just some sort of string. So we can convert it to a datetime object by doing the following. I can say dfDate is equal to pd to_datetime and pass in dfDate. And what this does is it's going to automatically convert this string to be a datetime object. And once it's a datetime object, that means I can extract information such as the month or year automatically. So I go ahead and run this. And now, if I take a look at my date column, note the formatting is different, and it now reports back that it's a datetime object, which means I can begin to perform feature engineering off of this. This datetime by itself may not be useful, but I can extract the year component and the month component. And the way I can do that is through a couple of simple calls. I can say df year is equal to dfDate, and I can apply a function that actually extracts the year from this datetime. So if I have a datetime object, it's simply an attribute call to grab the year itself. And I can do this with a simple lambda expression by saying lambda date and then say date month. If you're unfamiliar with lambda expressions, that's essentially shorthand for a function. So to show you what I mean by that, this lambda expression would be the exact same thing as if I did this. We'll create a function called year extraction, takes in some date, and then it returns back date.year or date.month. And in this case, this should actually be year in order to match up with what I'm calling the column here. So this lambda expression is the exact same thing as running this right here. So recall that when built in Python, you have this datetime object, and you can grab the attributes of year, month, etc., which is why we called pd2datetime on the original string column. And then this lambda expression is essentially shorthand for that. And I'm going to copy and paste this for month as well. And this is essentially feature engineering, because these features were technically hidden inside of the string date. And now I'm creating new columns to try to extract or engineer more information off my original features. This is a very common step, especially with timestamps. So we'll go ahead and run this. And now, if I take a look at the head of my data frame, I have this newly formatted datetime column, and I'll scroll all the way to the right here, and I should see my new year and month column. And now I can do some sort of exploratory data analysis to see if these are useful features in general. So let's go ahead and see if there's any variation based off the month that this is selling at. So maybe we price things higher if we believe they're going to go on market in December versus in March. So I can do that by saying SNS box plot. And let's go ahead and see the distribution per month. And another way I could do this is through grouping by month and then doing a describe on the price column as well, which is essentially what a box plot does visually. And let's make this just a little larger. We'll say PLT figure fig size, make this something like 10 by 6, go ahead and run this, and I can see the distributions here. Now, it's hard to tell just from this plot whether or not there is any significant distribution differences between the month that you're going to sell this house at. And what might be easier to do is just see the numbers themselves. So I could do df group by, call month here, and then just see what's the average price per month. So I'll take the mean after I do the group by, and then just explore the price. And then here, this maybe will allow me to actually see or read the numbers myself to see if there's some sort of significant difference between the months. And if I want to see this visually, I could also just call .plot, and this would show me the behavior. So it looks like maybe there's some sort of difference between the months. If we actually see the total wide range, it only goes from 5 million-ish to around 5.5 million-ish. So not a huge difference here in the price. Excuse me, actually 510,000 versus 560,000. So not a huge range, but it looks like there's some behavior differences there in the months themselves. And we could do similar things for the year. So if I wanted to explore the year, this plot definitely makes sense because if you look back at King County sales, they're just increasing in price as time goes on. And you would expect that just naturally with inflation, unless there's some sort of a major housing event. Okay, so we featured engineered year and month. We'll go ahead and just keep them in there, see if the model uses them or not. And we'll drop out our date column. We'll say df is equal to df.drop, and we'll drop off that original date column since it's no longer useful to us since we featured engineered what we. Now let's take a quick look again at what remaining columns we have. We can either do this with df columns, or I can simply just check the head of my data frame to begin exploring this. A lot of these features actually make sense already the way they are. So number of bedrooms, bathrooms, square foot living. Doesn't look like we have to do a lot of feature engineering here. And even the waterfront and view type categories, those are already in dummy variable form for us. So it's either a 0 or 1. Something that we want to maybe take note of is this zip code column. So notice this zip code is numerical. And if we feed this directly into our model, the model will assume that it's some sort of continuous feature, that somehow zip code 98178 is greater than 98125. And this may or may not be the case depending on how the zip codes are actually mapped out on a real map. So this is where domain experience comes into play. You'd have to either look up the maps yourself, so you can do a quick Google search and find some sort of zip code mapping on top of King County and see if there actually is a relationship. You could zoom in here and see if there's a relationship between the numbers zip codes are assigned versus maybe their latitude or longitude. And you can also do that through some sort of correlation plot. But if you take a closer look at this, there doesn't seem to be a clear continuous distribution of these actual zip codes, which means you would want to start treating this as a categorical variable. So again, we'll come back to our notebook here and begin exploring this and see if it's actually viable to keep it as some sort of category. So we can say something like df zip code and call value counts on it. And this will give us an idea of how many actual unique zip codes we have and what their distribution is like across the data set. And it looks like we have 70 unique zip codes. So this is probably too much to just call PD get dummies on this and then have 70 categories of zip codes. So we'll go ahead and for this particular case, we will drop the zip code column because 70 categories is just too much for us. However, what we could do is with a little bit of domain experience and domain knowledge, maybe try to categorize this based off what we know are expensive zip codes versus maybe less expensive zip codes. Or we could do some sort of mapping or grouping to do zip codes in the south, zip codes in the middle, and zip codes in the north, east and west, etc. But this will take then a lot more manual work here, and it also takes a lot more experience of what King County is actually like. So again, a big part of machine learning and data science is to contact someone with domain experience and try to get those mappings and feature engineerings in place. But for our use case, there's 70 categories here. We'll go ahead and just ignore them for now. However, in a more realistic situation, you would probably want to take the time to look at a map and start mapping these out yourself manually. So we'll say df is equal to df drop, and kind of for the sake of time really, we'll drop the zip code column. And then there's other things we can take a look at. Another one that may be kind of troublesome is this year renovated. You'll notice that year renovated, if we take a look at it, df year renovated, let's do a value count on that. Most of the values are actually 0, which essentially implies that it was not renovated. So you're just stuck in a 0 there. And then we have 2014, 2013, etc. Now there's different approaches we can take here as far as feature engineering is concerned. One main issue here that we can tell is that 0 is not actually a year. Instead, it's basically an indication that the house was not renovated. So it may make more sense to categorize this as renovated or not renovated. Essentially, turn all these years using a custom.apply function into a kind of positive renovated call, and then keep 0 as just not renovated. So we could do that through an apply function. However, we can actually take advantage of the situation by thinking of it in the following fashion. Notice that it's most likely the more recent the year of renovation, essentially the higher the value of this year renovated, then the more likely that the house is going to have a higher sale price. And we can just think of that intuitively because the more recent the renovation, the better. And since 0 actually follows along with this correlation, it's almost like the lowest year possible, then we should expect that to also have little value. So in this case, we're actually kind of lucky, and due to the scaling from 0 to the highest year, higher should correlate with more value, and we can actually just keep this as is. And that's essentially the kind of lucky situation we find ourselves in, that the years happen to go in a positive direction, and the higher years tend to correlate with more value, because the more recent a renovation, just intuitively you expect that to have more value. Now, that won't always be the case for things that are years and then have zeros filled in, but in our case, we got kind of lucky here, and that makes sense to just leave it in. However, you could perform more feature engineering off of this by categorizing it into renovated versus not renovated. Okay, and then other things we can do is we can take a look here at something like the square feet in the basement, kind of a similar situation. So if I take square feet in basement and do value counts on it, you'll notice that in a similar situation, it just has 0 there for a lot of the entries, and 0 most likely just means there is no basement there. So they just put in a 0 for square feet in basement. Now we can see here, again, the values starting to go upwards, etc. And these also basically make sense as a continuous variable, because we would expect that if there is no basement, it would have less value than having an extremely large basement. So we can also keep this as is. So a lot of times you'll have to make the decision in feature engineering if you want to make a continuous variable categorical or just keep it as continuous. And you have to really think carefully if it's valid to keep it as continuous. And for these two, it's not a crazy assumption to keep them as continuous and leave these zeros as kind of your bottom marker. All right, so that's it for our feature analysis and feature engineering section. Later on in your section exercise, you'll be doing a lot more feature engineering than what we've done here. So keep that in mind. Feature engineering and exploratory data analysis is pretty much always a necessary part of any good data science or machine learning project. Coming up next, we're then going to focus on doing our train test split and scaling and pre-processing our data in order to create our model to run off of it. Thanks, and I'll see you at the next lecture.